So first of all, we'll start off with talking about VSEPR. So the VSEPR theory is otherwise known as the valence shell electron pair repulsion theory. And so this basically talks about our 3D structure of molecules and how they are arranged in space, as opposed to it being a Lewis diagram. And so as we can see here, on this particular diagram, we can see that we've got a methane molecule, and then we can convert it into a VSEPR theory in which it forms a triangular type molecule shape. And so these are going to have these structures based on non-bonded atoms avoiding each other due to mutual repulsion of their bonding electrons. So this is talking about where certain non-bonded electrons don't want to be nearby each other, so they will evenly spread each other out because they're repelled by each other's electrons. Then we can also consider the bonding electrons, and they're repelled by lone pair electrons. And so that's talking about where we have a lone pair of electrons which aren't bonded to anything else, and they cause a bend away from the rest of the molecule because these particular electrons repel the rest of the molecule due to the electrons in the other parts of the molecule. And so these lone pair electrons are also going to be repelled by other lone pair electrons. So if you have multiple lone pair electrons in a molecule, then they're going to be repelled by each other, which further pushes the rest of the molecule away from each other, but also pushes those lone pairs away from each other, which is also going to affect the structure and bonding of the particular molecule in its 3D structure, compared to where we look at the Lewis structure, which is very 2D and just a flat representation. And so we need to consider degrees of repulsion. And so these degrees of repulsion are going to be dependent on these factors which we spoke about earlier, where we considered the non-bonded atoms, the bonding electrons, and our lone pairs. And so the effect of the additional repulsion from those lone pairs is going to be demonstrated by differences in bond angles, and we can specifically see this here in methane, ammonia, and water. And so we can see with methane, we've got this 109.5 degrees separation of angle between the hydrogens which are bonded to our central carbon atom. And so this is because all of the hydrogen atoms around the central carbon have evenly spread themselves out such that they've all attained an 109.5 degrees between each other. And this is because there's 4 hydrogen atoms which surround the carbon atom, and so because there's 4 of them all surrounding this one carbon atom and there's no lone pair to repel them away, it's going to result in the molecule being structurally even in its 3D structure. We can then consider ammonia, and ammonia has an 107 degree angle between each of the hydrogen atoms that are spread flat or slightly downward angled from the nitrogen. And so this is because ammonia has a lone pair from the nitrogen atom. And so that's because nitrogen has 5 valence electrons, but we can see in ammonia, hydrogen has only been bonded 3 times. So there's only 3 hydrogen atoms bonded to the nitrogen in ammonia. And so this means that all of the hydrogens have achieved a stable octet because they've only got 1 in their valence shell. So if they bond with nitrogen, they've then completed their valence shell of the first valence shell to have 2, which would achieve what we call a stable octet. But with the nitrogen atom, it would need to have more atoms to bond to it in order to bond to the two atoms on the top of the molecule which remain. So obviously nitrogen has 5 valence electrons. It's achieved an extra 3 from each of the hydrogen atoms, which gets it to 5, which gets it to the stable octet. However, there's 2 unpaired electrons, and those 2 unpaired electrons are sitting at the top of the ammonium molecule and are repelling the hydrogen atoms of that molecule because they don't want to be near that because of the repulsion theory. And so that forms this downward structure where the nitrogen electrons on the top from the lone pair repel the hydrogens downwards. We can then look at water, and so water is just H2O, so we've got our central oxygen atom with a hydrogen bonded on either side. And so this has a 104.5 degree angle, and that's because there are 2 lone pairs. So that's because we have the valence electrons in the oxygen mean that there's only pairing for 2 of oxygen's valence electrons, and so that leaves 4 unpaired electrons. And so these 4 unpaired electrons are sitting at the top, they're repelling each other, and so they will sit angularly on either side of the oxygen atom, but then they're also repelling the hydrogen atoms which are branching off from the oxygen, and so hence pushing them downwards, forming in that 104.5 degree angle. And so that's important to notice that we have a trigonal pyramidal bond angle, which is that 109.5 degree angle, which we can see in methane. With water, we can see that that is a bent arrangement, and we can see we have a similar pyramidal type arrangement with ammonia. And so even though the parental geometry is the same, the overall geometry differs due to the electron pairing. And so the bond angles have been shortened because of the presence of lone pairs. And that's just because of our repulsion theory, where the lone pairs push the rest of the atom away, shortening those bond angles. So we want to learn how to draw Lewis diagrams using VSEPR. And so the fundamental process of doing this is not that difficult. We just want to first focus on drawing the Lewis diagram and then understanding what the parental geometry is in order to then understand the repulsion that's occurring in these molecules. And so the first thing we want to do is determine the correct Lewis diagram for the molecule. So it doesn't need to be the correct shape, it just needs to show all of the atoms and what is going to be bonded by what. We then want to determine what the parental geometry is. So that's understanding where the bonded atoms are going to be located and where the lone pairs are going to be located. Because it's important to understand what is bonded to what so that we know where things can disperse off, and also we want to understand if there are lone pairs present, because we want to know if there's 1, 2 or no lone pairs, as this will tell us the degree of repulsion which will occur and whether the molecule will bend in such a way that the bond angles will decrease. We next want to then chop off the arms where the lone pairs are in the appropriate places according to our rules that determine molecular geometry. So that's understanding where we need to remove things in accordance with those lone pairs. And then the final thing is we want to consider the added repulsion of the electron pairs. So how the electron pairs are causing the repulsion and to what extent they are causing repulsion due to how many lone pairs are present. So these are our molecular geometry types. And so these are all of our bond angles and the molecular geometry names, and then a little diagram to represent what they will look like. So we can see our first one here is a linear molecule. So linear molecular geometry has a 180 degrees bond angle. And so this is our molecules where they're completely straightly bonded to each other, and there is complete stable octet that's been attained without the presence of any lone pairs. So this means that the molecule in pink in the middle on the linear bond angle is a different atom to the white atoms, but they've all bonded in a straight line and have used up all of their electrons in order to bond together, and so have no lone pairs, so there's no repulsion, so there's no need for the molecule to bend away from anything because there's no repulsion coming from a lone pair. And so this just means that the molecule stays completely straight. There's not really any bond angle, so we say that the bond angle is 180 degrees. Our next one is bent, and so the bent molecular geometry is looking at a 104.5 degrees bond angle. And so a 104.5 degrees bond angle is typically going to suggest that we have 2 lone pairs present. So that means 4 unpaired electrons. These electrons pair up and form 2 lone pairs, and so these sit on either side of that central pink atom and repel the white atoms downwards in such a way that it forms a 104.5 degrees angle because the lone pairs are repelling those other atoms. And so this is something that we see in water, which we looked at a bit earlier. Our next one which we see is trigonal planar. And so trigonal planar has a 120 degrees bond angle. And so we can see that this is another, much like the linear molecule, there's no presence of unpaired or lone pairs in this particular scenario. And so we don't have any downward repulsion that we can identify in this molecule. And so as a result of this, the molecules are spaced evenly from each other all around the central atom. So the central atom being the pink atom. And so they're all spaced evenly around, resulting in this 120 degree bond angle between all of them because they central around in a circular pattern, and so all of the angles around the central atom add up to 360 because there is 3 atoms surrounding all angles, that can be divided by 3 to get 120. Our next one is tetrahedral. So tetrahedral has a 109 degrees bond angle, and so that's because much like our linear and our trigonal planar, there's no presence of a lone pair, and so this means that all of the atoms stay centrally located around the central atom, and so we can see that they all branch off at an equal distance around, and so this equal distance around means that we don't have to worry about any changes or any repulsion. Our final one is the pyramidal arrangement, and so the pyramidal arrangement has a bond angle of 107 degrees between each of the branched atoms. And this is because we do have the presence of a lone pair. And so this is quite commonly seen in ammonia, where we have that lone pair on the top. And so what the lone pair does is it repels all of the atoms, all of the white atoms, which we can see, downwards from that central pink atom, because the lone pair on the top is repelling them downwards, and because there's obviously electrons in those white atoms, they're being pushed downwards because they're repelling, because like is going to repel like in this case. So now we just have a example question. So if you're watching this live, feel free to take a moment to try these out yourself. So we'll just give about 1 minute for you to try these out yourself to figure out what the molecular geometry and bond angles of the following molecules are. And then if you're watching the recording, then feel free to take this time to try these out on your own and pause the video if you need. But basically we want to determine what the bond angles of CH4, NH3 and H2O will be. So I'll give you about 1 minute to try that on your own. Okay, so that's about 1 minute up. So these are our answers here. So we've got CH4. So CH4 is otherwise known as methane. And so this follows a tetrahedral type shape. And so it's going to have 109.5 degree angles between them. And so we can see this here. We have our Lewis diagram, which has then been converted to show our 3D arrangement and show our bond angle. And then we've also got our VSEPR 3D model, in which we can see this tetrahedral shape which has been formed. Our next one is ammonia, or NH3, and so we can see that this has a pyramidal shape and has a 107 degree bond angle. And so with this here, we can see we've obviously got our Lewis diagram, and then we've got our 3D VSEPR diagram. And so we can see that we've got this lone pair here on the top, and this lone pair is repelling the hydrogen atoms downwards, and that is resulted in this 106 or 0.7, or rounded up to 107 degree bond angle. Our final one is H2O. And so this one has a bent structure, and that means that it has a 104.5 degree bond angle. And so we can see our Lewis diagram here showing the two lone pairs, and these two lone pairs have repelled the hydrogens downwards. We can also see that here in our 3D diagram, which shows that these lone pairs are repelling the hydrogen atoms away from them.